yesterday we were talking about maybe, just maybe, or not maybe, it's actually definitely, but I'm trying to lead you into it. It would be easier to plug into a linear equation, y equals mx plus b. Maybe it'd be easier to plug into a linear equation, y equals mx plus b, than to plug into the function the tangent line is coming off of. Tangent line. Why is it called a tangent line again? It hits at one point. And tangent, we learned in geometry, a tangent line is the one that skims at one point to a circle. But wait a minute, where else have we seen tangent before? Trig. Oh, like tangerine? Yeah. Why? Why might a tangent line be called a tangent line? Well, it's skimming a graph. Yeah, I know that, right? And it's, theoretically, every line that's slanted is going to go through an axis, right? So, when I'm talking about the 2 points, and I'm talking about the derivative, and the derivative is a slope. Question, how do you find a slope? Rise over run. And what is rise over run when you think about connecting with the right triangle 2 points? Isn't it the same thing as tangent? So in essence, technically, f prime of whatever x you're trying to find is the same thing as opposite over adjacent when you're making or joining. Interesting. But coming back, tangent, they do coincide. Oh, it's not me, it's this one. Sorry, I just did wrong. Let me turn it upside down. But maybe it'd be easier to use a tangent line instead of using the function. However, we did talk about yesterday, why is there a circle right here? Why did I do that? You remember? Are tangent lines good approximations everywhere? If I was to go over some x value and go up to the blue, is that a good approximation for the black when you get far away from the point of tangent? No. The tangent line skims, but kind of by definition, description, I don't know, just the nature of the beast, it's only going to stay close for that little part where it's skimming. You might hit somewhere randomly if this function decides to do something funny, but let me show you a cool application. Okay, this is what I want you to write in your notes. Real quick, an example before we even do, stop hitting buttons, my board is off. Someone hit it. Okay, better. What if I wanted you to use a tangent line, this is a quick example before we go grade our 3.6, to approximate square root of 9.3. Let's make sure phones are gone, especially if calculus has been a struggle lately. So I should technically be taking them for your sake. Okay, so approximate square root of 9.3. Yeah? Now most of you would be like, oh, whatever, 3-ish. I want better than that. I want the tens, maybe even hundreds. Oh, that's one. Killing me. Okay? Now, here's how we can use a tangent line. Now, hold on. A tangent line doesn't need to be tangent to somebody or something. We're going to make our somebody or something square root of x. Anybody know why? There's a square root in it, right? What's going on for the number? Oh, it's square rooted. Cool. And I'm going to use the tangent line at x equals 9. 4k. 9 is a perfect square root, I know, and it's really close to 9.3. Too obvious. Too close to 9.3. Or it is really close to 9.3, right? So, you guys, come on, be amazing. How do I find the tangent line? Go. Line. Equation of a line. Forever card. Come on. Forever final coming next week. Thursday. Study this weekend. Carry around your cards. Help. How to do an equation of a line. You guys are doing it. Tell me. Algebra 1. Equation of a line. Y equals mx plus b, but there's a better one for calculus. There's a better one. takes for me to drag things out of you, equals m times x minus x1. Who can I plug in? 9 is x1. What's y1? Square root of 9. Wait. Do you get it? X is 9. Y, isn't that f of x? Come on, don't forget algebra. Y equals f of x. F of 9 is square root of 9, right? Equals, how do I get m? Remember our forever card? How do we get m? F prime, right? The derivative. So f prime of x, first of all, is equal to 1 over 2 root x. Hopefully we kind of track with that. Bring down to 1/2. But I don't plug in an equation. I need a number. How do I get a number? Plug it in. Who? 9. 2 times 3 is 6. True? So let's plug in 1 6. Now, can we simplify? Yes. Y equals, I'm going to do a little bit simplifying here. I'm going to have that be minus 3. I'm going to add 3 to the other side. I have 1/6 x minus 9. This is the tangent line. Check. But now I need to use it. This is what local linear approximation is, or using a tangent line to approximate. We have a tangent line. How many of you guys off the top of your head can do that to tenths or hundredths or thousands? Not many. Probably if you're an American student, yeah, probably not at all. To be honest, other countries definitely work to get a better number sense than we do, to be honest, at elementary school. However, most of you are like, yeah, I don't know. But how many of you guys can plug into this? Plug what in? Well, what's our x value? We want this one. This one's close, but we want that one. Well, how do we get that one? We ask ourselves the question, well then fine, who is x? 9 point, not square root, because that's the f of, right? Who's x? 9.3. Where's there an x? Ha! 9.3. Minus. Now we use our equation. Now what are we trying to do? We're trying to approximate 9.3, which is a y value, which is going to be approximated by this tangent line's y value. Less. Aha. Now you're like, well, I've used my calculator for that too. Really? Hold on. Y equals 3 plus 1/6 times 9.3 minus 9 is 0.3, right? Well, then how do we do that? Well, it's 0.3 divided by 6. Ooh, 0.3 divided by 6. 0.3 divided by 6. Right? 0.3 divided by 6 is 0.05, so therefore I'm saying a pretty stinking good approximation for the square root of 9.3, which is 0.3, which is actually kind of a big distance away from our original point of 9. But still, let's see how close of an approximation it is. I bet it's good. Someone, calculator, go. Here's my calculus. Let's see how close I got. Well, you too, but really just how close did I get? Very close. 3.049. Ooh, look at that. This one is 3.049. Sorry, give me a couple more. 959. How close did we get? Pretty stinking close. If that's the actual value, and this was my approximate value, that was pretty stinking close, and we were 0.3 whole away. If we needed to do like 9.1 or 9.01, man, it'd even be closer. It'd be a better approximation. Now, if you go on in calculus, there are other ways of approximating better than tangent lines. Tangent lines are good really close to the point of tangency. There are other things we can use, actually parabolas and cubics and stuff that skim longer and are much, much, much closer. This is still working pretty stinking good. So when I'm talking about using a tangent line to approximate, I'm saying you can use some calculus to figure out stuff like that. Now, what would be the dilemma if I had square root of 10 or square root of 11? It's it's not close to a perfect square. So we are somewhat still limited, once again, by us being, to some extent, in introductory calculus, and only being able to use a tangent line in Calc 2 or Calc BC towards the end. You're able to start using Taylor polynomials, Maclaurin polynomials. Anyway, that's kind of fun. So you get to be better. But we're just starting out. So we're able to approximate anything that's close to one that I know perfectly. Does that kind of make sense? And we can approximate ones farther away, but as we saw in the picture, as you get farther away from a point of tangency, the approximation gets less accurate, so there's more error. Let's go ahead and really quickly, spirals open, 3.6. Didn't we work a lot on this yesterday? We covered like 3 questions. Yeah. We covered like 3 actual homework questions. We kind of went through each of them. To be honest, depending on what you had last night, if there was something that was way out of the ordinary, totally messed up your schedule and your time, maybe there would be an excuse for not having this ready today, but otherwise, if you guys didn't have this ready, I walked you through the majority of the homework yesterday. Either doing examples in class or giving you hints to start. If you weren't even able to do homework at that point, you might want to reconsider whether to stay in second semester. Really quickly, make sure everyone in your group is awake. But if you can't even do homework when it's being handed to you, come on, guys. We can do this, okay? But if you don't want to do this, you might want to reconsider whether or not to stay in. Just letting you know it's an option to leave. No hard feelings, a little bit of sadness on my part, but it would be okay. I'd get over it. I always do. Okay? All right. What was our first even? Number 8, is that right? Okay. There he is. Let me zoom in. If you want to check your equations really quickly, here was your clue. Here was your, hey, we're keeping them. Solve for one, plug into the other. Let's take a derivative. Da-da, set equal to 0. Solve. There were no endpoints. So guess what? Ha-ha, he was our answer. And we use him to find the other one. Yeah? Okay.
If you plug back in the 3 root 2 back into the derivative or back into the original, the first, like the x squared plus y.
If you plugged into the derivative, you would get like a rate or a slope, which you don't want. All you want is y itself, so you have to plug into the one with a y. Does that make sense?
Yeah, so when you're solving, with like when you're squaring 3 root 2, is it 9 times 2?
Yes.
Okay, that's right.
Yes, yes, yes. Because you would think 3 root 2 times 3 root 2, 3 times 3 times root 2 root 2.
Yeah.
Does that make sense? Okay, cool.
Yeah, back is fine.
Oh,
Back is fine.
oh, it's right there on the next to the cookies. Thanks, Cam. Tell her it's been going off a little bit. I don't know what's up. Okay, you guys got the final? So 3 root 2 and 36. And if you're like, wait, I didn't get 3 root 2. It's root 18 simplified, right? Okay. Keep going. Number next one. Uh-oh. We have one more even somewhere. 46. This was the funny, how do you see? That's not what I want. Hold on. 46. Wasn't this the weird, how do you see it?
Yeah.
Hey, guess what? I figured it might be a little confusing, so guess what I have waiting? Wait for it. Oh, where is it? Oh, did he get deleted? Oh, stink-a-dink. My computer randomly deletes pages, and I don't know why. Give me just a second. Nope, he's gone. All right, hold on. The how do you see it one was a little bit funny. Let me go ahead and let you guys look at the answer for just a second. I'm guessing most, if not all. Where's my remote? Oh, Sparkle. Gotta love you. Okay. I'm guessing some, if not all of you, missed at least letter D. I'm guessing some, if not all of you, missed at least letter D. Hence why I had this copied in your notes, but somehow he went away. Does anybody have any ideas why a file saved on a network would open one way on one computer connected to the network and open another way on another computer to the network?
On the default program on the different computers.
Because one program to be updated, like all the things to be updated on that computer could not be updated.
True. Good call. Okay. That's what I should check out. All right. So, here they are. Really quickly, how many of you guys got D right? Let me see. I can see in the computer screen, or the whatever this thing is, TV. How many got D right? Oh, see, it's a struggle. I'm not even asking the other ones because I really don't want to be depressed this early in the morning. However, D was a little bit hard, so hold on. Let's peek at him. Oh, now it's not copying and pasting. Even better. Yeah, A, B, and C shouldn't have been hard if you just looked at the graph, right? Increasing, decreasing, no big dealio. So what made D hard? There he is. Thank you guys for your patience. I really appreciate it. And understanding technology. When you don't have an admin password, it's a little funner. Okay, so, real quick. Profit, who's that? This thingamabob. Cost, who's that? That thingamabob. Question, where's the worst place to be if you were the owner of this company? Dishing out $60,000 for advertising and making no profit, right? Oh, that stinks. So if you're looking at this, you're like, oh, I don't think I want to end up anywhere here. True? You're spending more money and you're making less. Okay, so now this is just advertising costs for some of you that are like, ooh, that's a lot of profit. There's other costs too. But coming back, where is the profit increasing? Where is everything good going? From 0, it's going up, profits are going up. I'm spending more, but profits are going way up by way more than I'm spending, right? Okay, so it's good between 0 and 40, true? Where is the profit decreasing? 40 to 60. It's easy because this is the graph of profit, so it's like the graph of the original of F, and I'm saying, yay, it goes up, yay, it goes down. I mean, it goes down. C, I know the answer. C, where is the max profit? 40-ish, right? 40-ish. D, okay. This was just a quick little like, hey, business and calculus connect. Hence why there's a class for all business majors or econ majors or et cetera majors called business calculus. But if you pass this class, and if you don't got that one, maybe you don't got business, maybe you should change. But coming back. But you won't be scared of the calculus. Come back. D, the point of diminishing returns. Ooh, that's snazzy. People in econ, maybe Zuck will teach it to you. But it's the point at which the rate of growth of the profit function begins to decline. Estimate the point of diminishing returns. A lot of you would say, decline! But it doesn't say profit declines. What does it say? Rate of growth of the profit. Ooh. Rate of growth of the profit. How do I see rate on a graph? Tangent line. Change in y over change in x, which we can't do of the actual, that'd be average, we want instantaneous. Okay, tangent line. Wait a minute, isn't this part of the graph concave up? And concave down? There's a point of inflection. Concave up means what's going on with the rate or the first derivative? It's increasing, it's getting steeper. Ooh, but at the point of inflection, what's going to start happening? It's decreasing. So where does the slope, the rate of growth of the profit, begin to decline? At the point of inflection. Which, okay, it'd be a little bit rough if I'm standing, I realize it when I'm standing off the side, I don't see it so well. I think it looks 20-ish. Right? Give or take. Maybe you would have said 25 or 19, 18, something. But there's concave up and then concave down. And if it's hard for you to tell the difference, then try following it. Say, yay, boo. And right where it started to go blue, then there you go. Right? Point of diminishing returns, 20 as in $20,000. All right, cool kids. Let's go check those multiple choice real quick. Those are the last evens that you have, right? Did you have 52 and 54?
Yeah.
Okay. 52. What? It's a triangle. Do you guys get your triangle? You could have used Pythagorean theorem because it's a triangle. Pythagorean theorem could have been your clue with a number. Solve. I think somewhere it said y greater than 0. I don't really remember where. Okay. Maximum area of a right triangle with hypotenuse. Well, maximum you want positive numbers, not negative. I think that's where that was going. Coming back though. So you can choose the principal root or the positive square root for y. Area of a triangle is, a few people got this messed up last night and the night before, 1/2 base times height. Remember, it's a triangle. 1/2 base times height. Plug it in. Take the derivative. Sadly, you have to take the whole derivative. No trick this time because you have pieces on the outside and the inside. Take the derivative, get a nice... Oh, they didn't even get common denominators? Lame sauce, party poopers. Anyway, long story short, plus or minus root 72. We're choosing the positive to maximize the area. So 72 root is 6 root 2. Then plug it in to your clue. Where is he? To your clue to find y. Your final answers for x, for y, plug it in the area formula because they didn't ask for the dimensions. They asked for the area. 36. Cool? They didn't ask for the dimensions. They asked for the area. 36. The answer is C. Number next one, 54. We're trying to maximize. Ooh, but didn't we do one kind of like this yesterday to get ready for it? To maximize the area. So we have a clue that has a number. Hey, I think we're going to use him in just a little bit. And we need the area, but what's the area going to be of the rectangle? Kiddos, x, y is a point. Remember, x starts from the origin and goes out, right? So if I want the whole base, what is it? 2x. 2x, right? And then what's the height? Well, that's easy. That's just y. 2xy is the area. Plug in the clue right there. Simplify, rewrite, then take the derivative, set equal to 0, solve, and you end up with... What were they asking for? Ooh, they were asking for the maximum area again. So you take the x, you plug into the clue to find the y. There's your x, there's your y. Plug into your area formula. They were asking for area, not dimensions. Final answer is 500 root 3 over 9, and that matched with... Where's the matching thing? Oh, it was a short answer. Sorry, it was a free response, wasn't it? My bad. So then the dimensions, they asked for both. The dimensions are 50 thirds and 5 root 3 over 3, and then 500 root 3 over 9. You could have done decimals. I wouldn't have minded if they didn't tell you not to use your calculator. All right, kiddos. So do you have number 53 also? Okay, cool. We'll probably look at 53 tomorrow. Back to 3-7. We went over a lot of questions yesterday, the same ones that we started. You guys could have finished with the calc chat to check, not cheat, etc. 3-7, let's get back in. And one more time. With my little, you weren't even able to work on homework last night to get this section done. Except for maybe a few extenuating circumstances, maybe you should think of dropping. Please just know that said in love and care for you, knowing especially seniors. I know what your second semesters can turn into. And I really don't want to set you up for failure. Okay? But once again, I love you all. I want you all to stay if you're willing to keep working. Okay, coming back. I forgot that I didn't put a little bit of love in that statement earlier, although hopefully you guys know by now that I care. Okay? Here we go. Tangent line, we did that. We were like, oh, cool. Well, maybe not. I thought it was cool. To square root 9.3 and figure out a really good approximation to the 100th place. Oh my goodness. But let's go ahead and write down steps for what we did. Okay? Let's go ahead and write down steps for what we did. Let's go ahead and write down steps for what we did. Number 1, find the equation of the tangent line. That's technically what? Yeah. So I'm going to write it down. But it's technically a forever card. It's technically a review. That's why it's green. I'm not even going to go ahead and put it in blue. I mean, okay, the step is in blue. It's a part of this new type of problem that we're going to see. But it's review. We find the tangent. So y minus y1, yeah, we can start there, equals n times x minus x1. Just go back to algebra 1 for a second. Back when I used to teach it, I used to talk to them and be like, this is really important in calculus someday. You're preparing for when you're a junior or senior. Made a big deal about it. Your algebra 1 teacher probably didn't do that. I didn't teach algebra 1 for you guys. I taught it for last year's class. I got them in algebra 1, if they were here at algebra. But, coming back. It's okay. You learned it. You maybe didn't like it. You probably kind of ignored it and said, I don't like that one. But whatever, it's algebra 1, right? So then if they give you a particular x1, we could call it a c. Then we know, okay, plug it in, right? If they give us a function, they don't give us the y, no big deal, plug it into the function. F of c is the y1. And then if they give us an f of x, well, we can find an f prime and the derivative at c, not at x. Don't keep it an equation, you need a number, plug in that c, get a number, that's the slope, you got it. Okay? Y minus f of c equals f times c times x minus. Then, use it. If you're supposed to use a tangent line, then find the tangent line, then use the tangent line. And how do we use the tangent line? What did we do? Plug in. Plug in what? You have to figure out from whatever they're trying to find, or have you find, you need to determine x, right? Figure out what x is. Be careful. That last one, remember you wanted to use the square root. Some of you, the square root of 9.3, but the square root was the function. The x was just the 9.3. You have to determine the x value. For the approximate, or for what they want you to approximate, maybe I should say it that way. I'll give you the tangent line equation, which is going to approximate that function at that x value. And if we want to, we can name it something like x star. Sometimes they do that. Or C star, they sometimes label it or number it or whatever, but just figure out whatever x you want to approximate or use or need for the approximate, and then plug into the tangent line equation and simplify as much as possible. Now technically, could you use your calculators to simplify that plugging in? Yes. But the point is you wouldn't need the calculator like you saw me use the long division in order to figure it out. Couple more seconds, you guys got it? Since this came back, is it a quick reminder that the tangent line equation is an important one? Good, 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 good. Those forevers, they keep on coming. In the sense of, they keep on coming back. We keep on using them. So then, I want you guys to basically do what I did, but with a new example. Now, it's not super new. I still gave you a square root. It could have been something really cool, like maybe a sine function and make it fun. And have you approximate sine of pi over 8 instead of pi over 6 and use pi over 6. But let's just do a square root just to make it easy. Okay, let's walk through it. You guys have already seen me do one, so hopefully this can go fast. When it says find the local linear approximation, and they give us, now, they don't always tell you right away what you're approximating. Sometimes they give you the pieces and they don't make you find them. Like, they just give you right now f of x equals square root of x, and they give you the point of tangency. They call it x of 0, x of naught, the initial, whatever. They tell us 1. Are we approximating 1? No, because we know the square root of 1. What's the square root of 1? 1. He's easy, but what are we going to use him for soon? The square root of 1.1. Okay? All right, so local linear approximation. What are we supposed to find? A line. What kind of line? A tangent line, right? Okay, find me a tangent line. What should we do? Use the point slope formula. And we end up with. Okay, I can do it fast. I want to make sure you can do it. Find me a tangent line. What'd you guys get? Who went in? Ah, 1 did. What was over here? What? Why? Square root of 1. I'm going to write it because some of you didn't know it. Okay, what'd you do for here? Can we be cool and say we know the derivative of root x is 1 over 2 root x? Cool. Okay, so we ended up, hopefully, you ended up with y equals 1 1 plus 1 half times x minus 1. Cool? So now, when they say use that, now, it didn't say tangent line. This is something you have to realize. But what is the most important line in calculus unless it says average or secant? Tangent. How do we use it now? Where's he go? The rest stays the same, right? We're using a tangent line to approximate. This is the y of the tangent. Remember? That's the y on the blue line that was going off of the function. So it's not the same y value. If you have two different functions, you have two different y values. But we're using it to approximate the function, which is, so then plug and chug. What's 1.1 minus 1? 0.1. What's half of 0.1? 0.05. And what's 1 plus 0.05? Now it's not always 0.05, but we just happen to do ones where it was. Compare with the actual value if you guys want to see how amazing we were. 1.05 is approximately the square root of 1.1, which equals 1.049 what?
0.88.
Ooh, 88. We were a little bit. Oh. We still approximate. Okay. Pretty nifty. If some of you are wondering, wait a minute, why is this one farther off when it was only 0.1 away? Think about the square root function. As you get further into it, the tangent line will skim it more. As you come back and it's more concave or has steeper slopes, the tangent line will go off sooner. Angela.
If I had a complex fraction instead of a decimal, is that fine? Like if I had 21 over 20?
Yeah, technically. Like it's an approximation. I just like the decimals because we can compare it to our calculator fast. But yeah, it's okay. Alright. Now, this section, it starts with tangent line, local linear approximation. It ends with differentials. It starts with tangent line, local linear approximation. It ends with differentials. A differential, the idea is actually kind of complicated. Some of you have been asking me all year, what does dy dx? Not literally, maybe in your heads. What's dy dx? Why d dx? I don't get it. What's going on? Okay, I'm going to try and show you. I'm not going to go into tons of depth of it. Calculus came from basically the work of two different guys in two different countries. She's alive. We have Leibniz and we have Newton. Newton, basically probably a smarter guy. However, he was kind of introverted, or at least he wasn't very vocal. He liked to keep his discoveries to himself. Basically kind of figured out calculus. I think he was he the one doing orbits? I think he was trying to figure out orbits. Like with the planets and the movement and all the stuff, and he had to use calculus in order to help him. But he figured it out for his own purposes, didn't tell anyone. Other guy, Leibniz, whatever. He was working really hard, and he was like, "Yay, look, I did it!" And then Newton read it and was like, because it got published, and Newton's like, "You're wrong on a few things. Here, let me show you what I did." Some people argue as to which one was really first. Leibniz published first in some senses. Back then, it was harder, but Newton went ahead and was like, I already had this done and you made a few mistakes. But Leibniz was the one that came up with notation of dy dx and f prime of x and things like that. I don't think it actually did f prime, but we did dy dx. Newton just talked about infinitesimals and Leibniz decided to describe them. And here's what's going on. Okay? dy. You've been seeing it for a lot of the year. dy dx. And he's always referring to f prime of x. And what I just showed you over here is that a tangent line to a graph, a tangent line to a graph is talking about a change in y over change in x, but here's the dilemma. Why call it dy? Why not call it change in y? Remember how we were just doing tangent line approximations and how there is a y for the function, but there's also a y for the tangent line? Well, this starts to get confusing, right? Forget that this marker is a dead. Just pretend that you can see it. Okay, so pretend that. Oh, you see that? Thanks, it was an assist. Y equals mx plus b. Here. It was easier to work. Okay, so we have two different y's. Now it gets confusing. You have a y for the function, you have a y for the tangent line. Magnus was like, okay, hey, let's just change it a little bit and let you know it's for the tangent line and not for the function. So what did he do? He put a d. And what's that d mean? Basically, you're talking about change in y over change in x of the tangent line, but you can find it by going change in y over change in x of the original function secant line and make them infinitesimally close, let the change of x approach 0, we get back to the definition of the derivative. Okay, but all of that to say, in a sense, dy dx equaling f prime of x, the dy dx in a sense isn't necessarily tied together. It's not necessarily stuck together. Dy does signify the change in y of the tangent line for a certain change in x of the tangent line, and change in y signifies for the same change in x, so we can say these two are the same. Instead of going to the tangent line, it would just go all the way up to the function. So two different things, but they're both talking about change in x's and change in y's, but we just name them or we show them, we put notation that distinguishes, I was going to say differentiates, that's rough. All these English words I can't use anymore because they have mathematical meanings, but they're signifying change in y's for the two different pieces, one of the tangent line and one of the function. But here's the cool thing. We could technically find just dy by multiplying dx on the other side, if we were ever asked to find dy. We can split it up. Since f prime of x is dy dx, then we could say if we just want dy, well, no big deal, just multiply f prime of x by dx. Now, change in y would be a little different. If we wanted to solve for him, now this is a quick little, in a sense, parenthesis. But if we're in an actual application problem, change in x and delta x, they can stay the same. They're not the big difference. The difference is what function we're going to for the change in y. But change in y, well guys, you've been doing this since algebra, but it still could get confusing. Change in y is literally f of some x2 minus f of some x1. It's literally a difference of y. Just subtract two y's. What y's? The y's that come from the function. dy comes from a derivative. Change in y comes from subtracting two function values. Now, there are lots of applications. So many that I can't necessarily do justice to them in 3 minutes, sadly. We are going to see, don't put that away. We are going to see how to find dy and just practice with him. He's the easier one, but delta y goes into like calculating error for experiments and stuff like that, when it's too hard to do by hand, but we can cheat and use calculus to approximate. But so much so that I'm going to go ahead and 3-7 is due on Tuesday. But guys, we've covered part 1 and we'll basically cover part 2. We'll cover 2/3 of the section. So please, please, please get caught up, number 1, if you're not. Just remember my challenge, given with love. I want you guys to stick in there, or hang in there, but you need to do the work to practice. But this homework will be due officially on Tuesday. But we're going into 3-8 on Monday. And as soon as you see 3-8, you're not going to want to do this homework because 3-8 is way more fun. Well, he's 3-8. He doesn't really exist in the book. He's actually section 7.7 in the book, but whatever. We'll be cool like that. So, one example, just really quick. What's the difference? That's actually kind of could be funny, but you're not going to do it. What's the difference between dy and delta y? What's the difference between dy and delta y? One has to do with the tangent, a derivative, and one has to do with just the f of x. The one that has to do with the tangent, the derivative, is dy. We wrote on the page before, dy is equal to f prime of x dx. Who's my f of x? They said y equals, but that's my function, right? So then, all I need to do is find f prime, which we've been talking about a lot today, so we can just run there quickly, right? Derivative of square root of x, 1 over 2 root x. Multiply a dx. Guess what dy is? Generally. That one. Ooh, but they gave us specific information. What can I plug in to find it at this specific point? Yeah, because we know x is 4, and we know delta x is 3. So you go ahead and say 3 over 2 times 2 3/4, right? Is dy. Now, how different is that? Because I already gave you a hint that these can approximate each other. How different is that than delta y, which is f of x2 minus f of x1? Well, delta... Give me a second. 4 plus 3 minus f of 4. Y, start at 4, that's my point. Add 3, f of 4 is 7, root 7 minus root 4, which is going to be root 7 minus 2. You guys start picking up, anyone with a calculator? I just want to see how close they are, because our point today was can they approximate each other, and the answer is 0.646. Why, yes, indeed they can. Bye, cool kids. I'll see you later. Good work. We got a lot done. We just have a little bit more to do on Monday to apply this in the real world. Bye, cool kids. Hope you feel the sparkle tonight. Please stay safe, stay healthy, stay warm. If you didn't bring warm clothes, don't come to the sparkle until you get some. Take your vitamins. See you later.